My name is Sean Kavanagh, and I'm a PhD student in the groups of David Scanlon at University College London and Aaron Walsh at Imperial College London. And our research uses computational modelling techniques to investigate the impact of disorder and defects in solid-state energy materials. Today, I'm going to speak about some of our recent work looking at defect structure searching in semiconductors and try to convey the importance of accounting for this behavior in defect investigations, and also why this is particularly relevant in the case of perovskites. Okay, so by far the most common approach for modeling point defects in solids is the so-called supercell approach, where first we start with our relaxed crystal structure of the host material. We then generate a supercell of this crystal, which is large enough to avoid significant defect-defect interactions with neighboring supercells. With this supercell as our base, we can go on to generate the different types of defects that we'd want to calculate. For example, here we make a vacancy by just removing one of the red atoms like this. We then allow this structure to relax using DFT most likely, or any other total energy method, giving us our final defect structure. And then with this relaxed structure, we can then calculate the formation energy, which in combination with the structure gives us all properties associated with the defect. So the concentration, the transition level position, whether it's a deep or shallow defect, etc. So from the structure, we derive all properties associated with the defect. The issue, however, is that when we generate our initial defect structure in this way, before relaxing via some gradient-based optimization, as is done in essentially all ab initio defect studies, there's no guarantee that this will actually give us the true ground state defect structure. For example, this ideal undistorted initial defect structure could actually lie much closer to a local minimum on the potential energy surface as shown here, which would then give us a higher energy metastable structure, which does not reflect the true defect behavior. So when initially looking at this issue, we applied our structure searching method to a wide and diverse range of materials and their defects listed here. And we found this behavior to occur for defects in every material we looked at, where you get energy lowering reconstructions that are missed by the standard defect modeling procedure I just described, with a variety of underlying physical driving factors. The next question we might ask is, how important can this behavior be? Well, if we remind ourselves of the fact that the defect structure gives us all the properties associated with the defect, we can see that an inaccurate structure will give an inaccurate formation energy and thus inaccurate derived properties. So we're not the first to note this behavior, and here are a few examples from the literature where it had been found serendipitously or through blunt force manual searching with chemical intuition before. But what we've done is to try and show how prevalent this behavior actually is, which of course is something that you don't really know until you actually go looking. So along with this, we've built an automated workflow and package called ShakeNBreak to implement our defect structure searching method, which we find to work surprisingly well for its simplicity. I don't have time to go into the details of the method today, so if you're interested, please check out our documentation or papers on it. But in summary, it involves using a coarse scan of the defect potential energy surface in order to identify different defect structures or potential defect structures, and thus energy lowering reconstructions. And we've worked hard to make this package as user-friendly and automated as possible. Okay, so in our initial data set for testing our method, we had no perovskites included. However, from that initial data set, plus observations from many other studies that have since followed, we know that this reconstruction behavior is most likely to occur and be important when we have one or more of these features listed here. So, for example, a multinary composition, a reduced crystal symmetry, an open crystal structure, essentially non-close packed materials that have more space to distort, a mixed ionic covalent bonding, and or mobile ions with a dynamic crystal structure. The reason, of course, is that all of these contribute to having a more complex potential energy surface and thus a greater likelihood of multiple local minima on our energy landscape. So looking at this list, we can see that most, if not all of these features are actually present in perovskites, and so we expect that this behavior is likely very prevalent and very important in perovskites. Okay, so let's look at a few perovskite case studies and see if this expectation checks out. So I used ShakeNBreak on the prototypical and most studied double perovskite, which is cesium, silver, bismuth, bromide. And here we find major energy lowering reconstructions missed by the standard modeling approach in the vast majority of anti-site defects in this compound. So here ranging from around 0.1 EV all the way up to just under 3 electron volts. So really quite drastic changes that we're finding here. To have a quick look at some of the structures that we're finding when we use our method, if we take the neutral bismuth on cesium defect for as an example, for a standard unperturbed defect relaxation, we find that the bismuth atom sits essentially on the cesium site and forms these two bridging bismuth-bromine bonds with the neighboring bismuth and silver octahedra, and a slight distortion and perturbation of those octahedra. ShakeNBreak, on the other hand, finds that this bismuth atom likes to off-center a little bit, finding this displaced tetra-coordinated bismuth-bromine structure with a strongly off-centered silver atom beside it. That off-centered silver ion is not so easy to see in that initial structure, but if we look at it from this point of view, we can see here how significantly the neighboring silver atom has been displaced to lower the energy of this structure. If we look instead at the fully ionized bromine on silver defect, here we find our standard relaxation to give a pretty high symmetry structure with these two elongated bromine-bromine bonds, this octahedron, and then in the equatorial plane, the neighboring bromine atoms move away from our substitution site. Instead, ShakeNBreak identifies a much more distorted structure where the additional bromine displaces from the octahedron center and forms this sort of 7-fold coordinated bismuth structure with, again, an off-centered silver atom beside it. I should mention here, because a common question that we're often asked is if we enforce symmetry in our standard defect relaxation. And no, we do not. We have no symmetry constraints enforced in our unperturbed geometry relaxations, and we use the exact same calculation parameters for both cases, so for both the unperturbed and the ShakeNBreak relaxations, with the only difference coming from the initial structures supplied to our gradient-based optimizer in these two calculations. So the last example for this material is the neutral bismuth on silver antisite. Here, our unperturbed structure gives us a relatively undistorted result with basically a straight swap of a bismuth with a silver in one of our octahedra. Instead, ShakeNBreak finds a tetragonal elongation of this octahedron, along with, again, a displacement of a neighboring silver ion, again, lowering the energy of this structure. Okay, another particular type of perovskite that we've been working on recently, which I actually spoke a bit about yesterday afternoon at okay, let's just read, yeah, and then I'm moving it. Another particular type of perovskite that we've been working on recently is the vacancy-ordered double perovskite class, where we have found strong excitonic effects to be present. When employing ShakeNBreak to identify defect reconstructions in this material, again, we find a large number of energy-lowering reconstructions for the native defects with drastic effects on the formation energies. To quickly show some examples of the reconstructions we observe in this case, we can see here that for the fully ionized -4 charged titanium vacancy, a standard unperturbed defect relaxation yields a slightly contracted octahedron at the vacancy site, where ShakeNBreak identifies this iodine trimer structure, where one of the vacant octahedron iodines displaces toward the vacancy site to form these trimer bonds, lowering the energy by close to 1 electron volt. In the -1 charge state, where we have less electrons available and thus a greater propensity for forming these covalent bonds and essentially annihilating holes, we find again iodine trimers for our ShakeNBreak distorted lower energy structure, but in this case a double trimer with 2 of the neighboring iodines moving toward the vacancy position and forming these staggered trimer arrangement. And this is easier to see if I rotate the structure a bit like this, and you can see the staggered arrangement of our iodine trimers here. If we look at the antisites, for the fully ionized titanium and cesium defect, a standard unperturbed relaxation gives us this titanium-titanium dimer-like structure here with the 2 titanium atoms contained within a single iodine octahedron. Instead, ShakeNBreak identifies a much lower energy structure where the titanium atoms split and one of them goes to this nearby vacant octahedral site and pulling one of the neighboring iodine atoms with it. So the key takeaway from this whistle-stop tour is that symmetry breaking and energy lowering reconstructions are prevalent across defects in essentially all solid materials, and that this behavior is crucial to obtaining accurate predictions of defect properties. This is particularly relevant for perovskites due to their multinary composition, reduced crystal symmetry, open and dynamic crystal structures, and presence of both ionic and covalent bonding, all of which contribute to having a more complex potential energy surface and thus more possibility for local metastable minima. With that, I have to give a huge acknowledgement to my colleague, Araya Mascara Louise, as it was through supervising her master's project that we got to test our defect structure searching ideas out. And she's now pursuing a PhD in Professor Aaron Walsh's group at Imperial College London, and is absolutely one to watch for the future. Big thanks as always to my mentors, David Scanlon and Aaron Walsh, and you all for your attention.